I've started the live stream just so everybody's aware.
Oh, it is up
I
till
just
almost
started the
noon.
live stream. I'll start the recording in a moment too.
As soon as you do,
Although-
I'll share my screen, Pete.
Okay, I can go ahead and
Pete?
start the recording. Yeah, Angela.
I do have sharing ability, right?
I can. You have to make you a host, but yeah, hang on once.
I should have asked that earlier.
That's okay.
Do I
You
need to
already know.
restart or anything, or do you give me?
Nope.
Got it.
It's just a matter.
Angela.
I have to make you a co-host.
What will we? Where do you want to fit into the discussion? What point?
So I want to talk about a little bit about the hail last night. So in the southeast.
No, okay.
So you just let me. It's not very long. It's like maybe 10 minutes max, but you just give me the clue where you think it fits in within your storyline. I'm guessing it's before you go, Michael, since it's not necessarily since it was
That
in the
works.
past.
That
Okay.
works.
Great.
Yeah, that might be one of the best places. There might be another one too, Ange. If I'm in the middle of mine and I say, you know what, why don't you talk about it now? Would you be able to do that?
Yeah, I have everything queued up, ready to go. So just whenever is
Okay.
fine. Yeah.
Okay,
Excellent.
great.
I'm going to go ahead and start the recording here.
Okay.
All right, I'm going to share my screen then.
Sounds good, John. Thanks. I guess we can start whenever. It's 12 o'clock. So
I think I only have desktop one, Pete, but I might have some problems. I don't know what's going on with that. Okay. What a pain in the neck. I don't understand how to. This is not like sharing a screen on the other devices that we use. Okay, so let's see if I can get this to go the way I want it to. So here's our satellite movie over the. I'm not going to show the week-long one today because I've got other things I'd like to show today. But here's the satellite movie over the continental U.S. and adjacent waters from the last 12 or so hours. And there's a couple of interesting features I think I want to point out. One is, and Angela Rao is going to tell us a little bit about the history of some of the weather that you can see scooting across the southern states, particularly aggressively last night and now kind of decaying a little bit as it moves further east. She'll tell us more about that later. That is actively and still precipitating and was certainly so last night. The cloud mass to our north and west, however, is not, at least in the radar range of the United States, the Dakotas, Nebraska, parts of Minnesota, did not demonstrate much precipitation falling out of that cloudiness. I don't know what the case is over Ontario, so maybe there'll be some more information on that as we go. A really pretty intense, but not really unusual storm developing south of Greenland at the mouth of the Labrador Sea. I'll spend a few minutes talking about that from a Viz 5D perspective, because it's a storm that looks like it could occlude, but there's reasons why it does not. And those reasons have something to do with the downstream cyclone that you can see off the Greenland coast. So there's a series of waves here, and the stretching deformation is just a little too much for either one of them to really wrap itself up. And I'll show you some evidence of that. And then finally, an interesting feature that we'll spend a little bit of time on is, as you can see, clouds from this perspective streaming along the British Columbia coast in this movie, and then spreading cloudiness over much of Idaho, Washington, and Oregon. And some of that at high elevation is snow. Some of it even at low elevation is snow. And then it's raining across in showery weather across the Pacific Northwest. But this is an interesting feature that develops on the eastern periphery of a large anticyclone that sits in the Gulf of Alaska. And it may be quite similar to some of the features, this feature here is quite similar to those that developed in the northwesterly flow in mid-February and then came across Texas and the desert Southwest and gave them the precipitation that fell during their cold freeze. And so we had an iced over Texas for much of that week of the 11th to the 17th of February. So that's kind of interesting. I'll say something about that. So that's the broad roadmap for my portion of the discussion today. Beautiful sunny day here in Madison. We had our monthly high on Tuesday of 46 degrees. The minimum for the month was minus 18. And we were just commenting that a 64-degree temperature range over the span of a 4-week long month is pretty intense, but it's probably not unusual. I would guess that in the winter months, we get our largest difference between maximum and minimum for the month. And it might be interesting to know which calendar day of the year has the greatest all-time maximum, and then what's the biggest difference between all-time maximum and all-time minimum for a single day in the calendar year. I don't know what that is. I've long wanted to do that, and I've just never sat down to do it. It would be kind of fun to find out, at least for selected cities across the country. But something in the range of 60 to perhaps even 70 degrees of a difference is probably likely, and it almost certainly would be December, January, or February, is my guess. So that was interesting about our own month. And we're going to round it out. We're currently 12.6 degrees below normal through the 25th of February for Madison. And we are likely to stay certainly below 10 degrees below normal. And that's one of the coldest months in a long time here in town. Unfortunately, I don't have the information about just how long, but I'm sure it's quite a long time. So pretty interesting. So let me show you the distribution of weather systems across the country by virtue of Alicia Bentley's fine maps that you can find on the internet. This is, I think it's from 12Z this morning. Yeah, 12Z on the 26th, and is showing in shading the 200 millibar wind speeds. The red and blue dash lines are 1,000 to 500 millibar thickness in decameters, and then the black lines are sea level isobars. And so we have a jet on the eastern periphery of this big anticyclone that's sitting in the Gulf of Alaska. That's 1,044 in the middle of that. Yes, 1,044 millibars. So it's really quite an impressive low-level anticyclone, and the consequence is, and it's embedded within a large-scale ridge at 500 millibars, which we'll see a little bit later on. And so the tendency is for the jet to be retracted to the east over the Pacific and then deflected wildly to the north. So it grazes the southern part of Alaska. And then here's the northwesterly flow off the British Columbia coast, which is sort of a seed bed for the development of little weak disturbances that come down in it, one of which is affecting the Pacific Northwest today. And you get a hint of it in the 1,008 millibar isobar over central Washington state. There's a little bit of a depression there. It's at the exit region of the jet and a region of geostrophic cold advection. All of those things are working towards a little bit of surface development, but it won't last. And I'll show you evidence for that as we move forward. Okay.
Hey, John, just in the chat, Ben Johnson shares that as of the 22nd, Valentine, Nebraska had a 103 degree temperature range for February. International Falls was an 87 degree range. So
outstanding detective work, Ben, on the fly. And that's really great. So we should probably try and catalog. Valentine would be a great city to put on your short list. Minneapolis, of course, would be a good one. International Falls, just a whole bunch of regional stations, and just see what is that all-time maximum. I bet it's in the Mandan Nation, no doubt. The Dakotas is going to be where you find your worst extreme in the U.S., and it might even be worse in Alberta or in Saskatchewan in Canada. So pretty cool. Thanks, Benji, for that. Then let's go to the West Coast satellite. A little bit of an unusual order today, but there's a reason for that, as we'll see when we get going. I got to start it. Sorry, I stopped them all so that it wouldn't misbehave on me. So here's evidence in the satellite of the fact that there's no organized cloud systems in the Gulf of Alaska, except on the far western periphery of it. And that's a function of the presence of 1,044 millibar high sitting there over that portion of the country. But look at these clouds streaming along the British Columbia coast. You can, first of all, you can see if you look closely, some popcorn type cumulus. That's indicative of cold air at upper levels. And the cloudiness seems to gain a little bit of organization in the middle of this movie. Here it is spreading across Oregon into Idaho from southeastern Washington. And that's indicative of the fact that something's getting organized in the upper troposphere. And it's an upper tropospheric baroclinic zone, which turns into a sort of an upper level vorticity feature. And that spreads down into the interior of the Pacific Northwest. But we'll see that it doesn't last for very long. I haven't really done the diagnosis for why. I have some suspicions, but that's for another day. But it's a nice short-lived period of upper tropospheric frontal development and upper PV development. And we'll see that it just doesn't last very long. And on the eastern side of the giant anticyclone, you can see this flow of moisture. Here's the state of Hawaii. So that's the boundary of the tropics. And so you get a flow of moisture, obviously, manifest in clouds, headed from the central Pacific in the tropical regions up toward the Aleutian Islands. Not uncommon, but largely directed by the scale of the anticyclone that's sitting there off the west coast of North America. So pretty nice, somewhat unusual picture of the Pacific Pacific Basin. I like to see it more active, but it's always active in one way or another. And this is one of those modes of activity. Further to the west, there's the Kamchatka Peninsula. So we're well past the dateline. You can see there's a lot of cold air spilling out over the central North Pacific from Asia. And little disturbances are developing in it. We see them at oblique angles here, but there's one that's just west of the Aleutian Islands. Sarah Palin can see it from her house. There's some other cold air disturbances further to the west and extending further south. Okay, So now let's go to the radar summary. I got to start this one too. I'm trying to get smarter in my old age here. So here's the radar summary, and it really shows two stories. Here's the one in the Pacific Northwest, the showery precipitation that is now invaded all three of the states in the Pacific Northwest, Idaho, Washington, Oregon. It's raining at sea level in sort of the Seattle area, but it's snowing in a lot of other places around town, around that region. And you'll notice, when you look at this carefully, there's spacing between these cells. So these cells are just convectively, they're mostly convectively organized here. And so that's going to mean, rain for a moment in Portland, a little bit of sun trying to break through between cells, and then another shower of moderate to heavy rain. The other really interesting story is the precipitation that's organized here along, the southern Mississippi Valley extending into the Carolinas. Last night, it was a little more active convectively than it appears to be today. It's in fact decreasing in activity. The weather map discussion I prepared for my class had a little bit more of the orange and red reflectivity that you can see right at the beginning of this movie is beginning to wane. But Angela's got some things that she could tell us about this, the hail across the southeast associated with this boundary. I'll just say one more thing, Ange, before we transfer off, and that is, why is that giving me problems? That is, I'd like to just show this map, which shows the 850 millibar temperature in red and blue. So there's the 0 degree isotherm at 850, and there's the forecasted precipitation. And you can see that it does seem to pay attention. That is, the band of precipitation is not only oriented in a linear fashion parallel to the isotherms, but it pays attention to what seems to be a low-level frontogenetic boundary. There's flow that's got at least a northerly component in many locations, or an easterly component, as it does in central Missouri, but southerly flow to the south across the baroclinic zone. So my suspicion was that we had some weak, maybe modest frontogenetic activity in the lower troposphere that was at least helping to organize what might be going on along that line. And so, Angela, if you'd like to go now, we could, yeah.
I'm sorry, John, this is Michael. Just before you, the time for this map is what time?
Oh, yeah, this is 12Z this morning. And it's forecasted precipitation in the last 6 hours, ending at that time. Sorry.
All right, thank you. Thanks.
Yeah. So, Ange, if you'd like to go now, we could switch off, and then I could come back and finish the rest of the stuff I had planned, if that works for you. I think you're muted, so I can't tell what you're saying.
Thanks. I was going to say this. I'm going to take the sharing away from you, and hopefully this works.
Okay, I just did it myself. I don't know if anyone else can, but you should be okay now.
All right. Can you all see my desktop?
Yeah.
Yep.
Okay. So I just want to give the overview. So this is, I'm going to show a loop. I'm sharing my whole screen. So if any of this is too small, just let me know and I'll enlarge it. So I'm going to show a loop from GOES IR starting at about 1Z last night until present. And I think this kind of gives a nice story of, the convection was already ongoing in this region, but this gives you a little bit of idea of what we're looking at. And the slow progression and the upstream development of the convection as the night went on along that boundary. And you can see also with time, the weakening of the convection as it moved over towards the southeast, as John had mentioned today, with the weakening at times. So I'm just going to run through that just one more time. You see the most intense convective activity kind of over northeastern Texas, building upstream, and then weakening as we get into this morning. So what I want to talk about mostly is that initial period when we had some of the more intense convection. So I'm going to switch gears. I just threw stuff in a PowerPoint so I didn't lose where everything was. This was a pretty well forecasted event. You can see here this marginal area of convective activity that was forecasted by the Storm Prediction Center, kind of on this west-east oriented location ahead of what we'll talk about was a nearly stationary boundary. And for those who don't regularly look at SPC, they break down their outlooks into hail, tornado, and wind. So the story last night was an increased probability for potentially hail across this wide swath. So if we look at the verification, indeed, these hail reports, there were a few smattering of hail reports across Northeast Texas. And this triangle, this black triangle, indicates hail that meets the severe category or greater than 2 inches. So you can see the timing of this was around between 2:30 and 4 UTC. So this was just after 8 o'clock last night, where some regions in Northeast Texas experienced hail from some of those deeper cells. So social media is, the great resource to look for some hail reports. And you can see here some indicator. Thankfully, someone had their ruler out where you can see on the order of an inch or so in some of these locations, with the biggest hailstone a little over 2 inches. So this discussion is largely driven by some things we've been talking about in 453 and 753. So we've really been diving into analyzing soundings to think about the boundary layer and different stability layers throughout the atmosphere. So I want to show first last night the Dallas-Fort Worth sounding. So this was the 12Z sounding yesterday, and then the 0Z sounding. So remember, the hail occurred just a few hours after this 0Z sounding. One of the first things you'll notice is there's not going to be any indication of surface-based convection, pretty strong stable layer in the lower levels. So the thing to look for were these elevated steep mixed layers. So here you can see that the mid-level lapse rates were on the order of 8 degrees or so. So if you had some lifting mechanism to initiate the convection along these higher up and not surface-based, then you can access this instability that was present in the upper levels. So this was part of what was being forecasted, these steep mid-level lapse rates, as one indicator for maybe it could support some elevated convection. And in class, we haven't gotten too much into hail-specific parameters, but we know we need these stronger updrafts within the mid-levels to be able to support the hail growth. So that was over Dallas-Fort Worth, which is a little bit west of where the hail was formed. So then if we go over a little bit east towards Shreveport, you see a similar story. It's quite stable in the low levels, but you can see these steep mid-level lapse rates supportive of convection if we can get to this level. So this is just a screenshot of the IR image I showed before, where you can see these are the cooler temperatures. So these are the deeper convective cells. So in this particular case, it was this region that was producing the hail shortly before this time, or around this time, depending on which location. So we were able to find a mechanism to access that elevated instability. So in class, we've also talked quite a bit about radar signatures, looking at dual polarization. And for those who aren't as familiar, I'll orient you a little bit here. This is the Shreveport radar. This was at 3:25 UTC, so around the time of one of the hail reports. So here's the location of the radar in Shreveport. Unfortunately, where the hail fell is actually quite a bit of a distance between both the Shreveport and the Dallas-Fort Worth radar, but we're still able to see this cell with reflectivity exceeding 65 dBz, which could be a red flag for potential hail. But as we all know, reflectivity is most strongly dependent on the largest diameters. So we bring in differential reflectivity to look for potentially near zero values indicating nearly spherical or tumbling hydrometeors that could be an indicator of hail. So in this region where we have the highest reflectivity, you see there's a region of near zero ZDR. So this is a pretty classic hail signature from the radar perspective, looking at this isolated cell in this region producing some of the larger hail. So we talked about the hydrometeor identification, and this is one way that we can bring in the different dual polarization radar data along with a temperature profile to give us the indicator of the most likely dominant hydrometeor species in a radar grid box. So here you can see these reds are indicative hail. So forecast the steep mid-level lapse rates. We've got more nowcasting with these radar tools. This vertically integrated liquid is a parameter that integrates the reflectivity over a column. So you see these higher values in kilograms per meter cubed associated with this region where the hail is located. So I want to talk a little bit about winds, because I think this is starting to get at the story, is how are we able to access that upper level instability. So again, to orient ourselves, we've got reds away and green towards the radar. So near the radar, you see winds largely out of the north very quickly veering towards out of the east, and then the southeast as we get further away from the radar. So if we look at the velocity, the wind profile derived from the radar data, you see this turning of the winds with indicating this warm air advection over this region. So let's just take a look at what our lifting source was. And what we can see here from the surface maps, you see the strong temperature gradient and the higher dew points located behind this warm front. So it's this nearly stationary warm front that was very slowly moving across this region that provided much of the lift for this precipitation in this region. But one of the things you'll also notice here, there's this dashed orange line, and what this typically means is the indication of a dry line. And in class, we haven't really talked too much about the mechanisms of the dry line. But if you look here at some of the surface observations, you can see it's not necessarily as much of a temperature gradient, but a gradient in the moisture. So you can see some of the dew points behind that dry line here on the order of 30 some odd degrees, but out ahead, you've got a much warmer and moister air associated with this onshore flow from the Gulf. So this is all coming together to bring us to this area that supports the initiation of this convection, this elevated convection, and the necessary lift that we needed to access those steep mid-level lapse rates and the instability aloft. I think I'm getting a little bit long-winded. I'm just going to go into this morning. So that was last night. And after the passage of those storms, you can see from the visible satellite image, not long after sunset, this is at 1350 UTC, you can see the low clouds that are situated all over this region. And you can see this deep saturated layer. You can see the stable layer. So in class, we were talking about the nocturnal stable layer. So you can see this morning over to the Shreveport area, you've got these low clouds as the main precipitating area continued off and weakened towards the east. So what does that mean going forward? So this was the outlook for today. And as John mentioned, this is the focal point of a lot of that remnant activity. The lapse rates are relatively weaker today, so you were not expecting as high likelihood of hail in this region or as intense convection, as the amplitude of this mid-level trough flattens out a little bit as well. So that's all I have. It's a little bit quick, but this kind of nicely ties in some of the stuff we've been talking about in class, and we'll build off on when we get a little bit more into hail production in particular. All right, I'm gonna stop sharing and turn it back over to John.
Great, thanks, Angela. And it's great to get some activity in February as a harbinger of what's coming. That's going to be really neat to see some more in-depth descriptions of some of those things. I'm really looking forward to it. Thanks a lot. Let's see. I guess I'm going to try and see if this is what, this is what I want to show next. So let me share this. So I'm picking up now with the discussion of the current weather and showing where we were with respect to the Pacific Northwest. So just a survey of the current obs. I think this was at 11Z. So there's some snow along the Columbia River Basin in eastern Oregon, some snow across much of the northern part of the state, rain along the coast, light rain at Quileute, some other probably locations as well in the Puget Sound. So this is the showery weather, and then there's some snow in Idaho. One place has moderate snow right on the border of Idaho and Montana. So what's going on with all this is what I'd like to show next. So here's the broad scale picture within which this takes place. This is from the 12Z this morning. So here's isobars every 2 millibars. Tropical draws them every 2 millibars. I admire the desire to be dramatic, but it sometimes makes the maps a little bit messy. And then underneath is the 500 millibar geopotential height. I think that's every 60 decameters. So you can see this huge ridge sitting in the Gulf of Alaska, and right underneath, almost right underneath its axis, is 1,047 millibar high that's sitting there, dominating the weather in the Northeast Pacific Ocean, and as a consequence of the flow along its eastern periphery, influencing the weather over the Pacific Northwest in a fairly substantial way. So what I'd like to do next is I'm going to draw a one cross section and watch what happens along it over a period of maybe 6 or 12 hours. And that's going to be in the northwesterly flow along the British Columbia coast. So let's see if I can get that to work. Yeah. So here's the first one. And now you're seeing the 250 millibar winds that go along with that 12Z, 0Z map. Now I've gone backwards in time, but there's the ridge, 1047. So we're going to look at this cross section that is from northern Canada into the central eastern Pacific, right through the jet core as it comes in the northwesterly flow. So this is a cross section of the PV along that line from A to B, and the top level is 100 millibars. The dashed black line with the shading is the 2 PVU isotel, and then the dashed purple lines are isotax of the total wind speed, and then green is theta every 5 degrees Kelvin. So you see a pretty decent upper baroclinic zone. It's not a dramatically intense one, but it's got a fairly intense wind speed max of 100 knots. Right here associated with it. But the 2 PVU isotel is just a little thin tendril that comes down from about 350 millibars in a thin line in the shear line down to about 550 at this time. But what's cool is I never noticed I could do this before. I can march forward in model time along the same cross section. So you're going to have to carefully watch how this little box changes, because that'll show you where the 250 millibar wind max is. And the cross section line is going to stay the same. But when I go forward to the 6-hour forecast, everything looks different except the cross-section line. So here's the jet. The nose of the jet's made more southeastward progress. And look what's happened as you get closer to the real spot where the tropopause is folded in. The 2 PVU line goes all the way down to about 800 millibars in this cross-section. The jet max is now 130, and you've got this really intense upper tropospheric front, which you can see in the green theta lines, involving theta all the way from 285 up to about 305. So that's a really intense upper baroclinic zone. And then if I go ahead one more time, same cross section, jet looks about the same, but the whole thing starts to weaken, especially the baroclinic zone associated with it. So over a 12-hour period on the eastern side of this big upper ridge, there's a short-lived, pretty intense depression of the tropopause, and then it kind of recedes back to higher elevation. And I want to show you some of the manifestations of that in just a couple of images. So I found that was kind of interesting. This, I want to make sure I can update and get the most recent 500 millibar map, because when I put it together, it was old. Yeah, so here's the 12Z 500 millibar map. You can see the intense baroclinicity on the west coast of British Columbia and all the way down to about Portland. I'll zoom in a little bit. But it's, minus 34 in the interior, and this line here is the minus 25 isotherm. So it's not the strongest upper front you've ever seen, certainly, but the wind speeds indicate cyclonic shear and some weak geostrophic cold advection, but it's just a little bit of an upper trough there over the western part of Washington state. So if I show you the analyses from the model, the GFS initialized this morning, here's the 500 millibar vorticity strip that goes along with this development that we've been watching. And it's got its most intense values, something on the order of, 3 times the Coriolis parameter, right over and south of the Puget Sound in the Olympic Peninsula. So it's sitting right there. That's this morning at 12Z. And if I go ahead to the next time, I think it's just 6 hours ahead. Yeah, 18Z. Look at how dramatically weaker it is. So we're catching this thing both by the cross sections that I showed before and by successive horizontal maps. We're catching this vortex structure, which is really just the subsidence of the tropopause, receding back to higher elevation in the column. It doesn't mean that this wave will not be of substantial weather producing influence. In fact, at the prior time, I think it's immediately down shear of this region of upper vorticity where you have that developing cloud band that we saw in eastern Washington, Oregon, and Idaho that's spreading snow and rain in those locations. But it's when you move forward in time and the tropopause starts to be pushed back to its normal elevation, I think because of the nature of the vertical circulation, you start to lose some of the cyclogenetic potency of this development. And so I just wanted to show you that and it would certainly be worthy of further investigation to see just what happens next. And perhaps Michael will pick that up in the forecast to some degree. The last
John?
thing, yeah, go ahead. Sorry.
Excuse me. I'm wondering how much, is there a way to I guess there is a way to disentangle the loss of vorticity in this 500 millibar map due to column shrinking, or not stretching but shrinking as it goes over the mountains out in the west, as opposed to the recession of the uplift of the tropopause. The tropopause receding back up into the higher level.
Yeah, there probably is a way to do that. I mean, we're going over a couple of the 14,000 foot peaks. Mount Rainier is one of them, and then Mount Hood's about 11,000 feet. So we're getting close to about 500 millibars at the tops of those. So there is some influence of orography. One way that one might do it is find an isentropic surface that you think is well above the orography, and just watch what happens to the PV contours on that isentropic surface. Sometimes either the aerial extent or the actual values, depending on your contour interval, will start to change when there's a recession back to higher elevation. And in that case, you might still have a bit of the problem of untangling that, but at least that might be a little bit less of a confusing picture of what you're trying to see there. Right? But that's a really good point. There is a combination of those things going on. So I don't know any more than I've shown you today with this. So what I'd like to show you next is a little bit of information about this storm that's out over the east of the maritime provinces of Canada at the mouth of the Labrador Sea. I think that's going to mean I have to share another part of my screen for some reason. I don't really know how to share my entire screen. So let me do that and see if I can't get to where I need to be. I think it's right here, and then I'll probably have to do this again. So, but anyway, this ought to work. So now you can probably see this map of the North Atlantic, I hope. Sea level isobars at 12Z on the 26th. So here's the sea level isobars in black. This is the Alicia Bentley map again. Here's the jet shaded in, and then a strong thickness gradient where thickness goes from 540 decameters or lower in blue to 546 and higher in red. So this is the 984 isobar. So that means that's 988, 84, 80, 76. So this thing's below 976 millibars at the mouth of the Labrador Sea this morning. And we want to watch how it evolves for a short period of time. Here's Environment Canada's depiction of it in the infrared satellite image. And it's really noteworthy that there's vastly different cloud top heights in this image. And that's not uncommon. I don't mean to suggest this is an unusual storm in that regard. But the warm conveyor belt path, if you will, has the higher cloud tops, and they're colder. They're radiating at colder temperatures. And then you only get a sprinkle of those colder temperatures occasionally in the northwest or occluded quadrant of the storm, depending on whether or not it's occluded. But it's a nice example of a storm in its kind of classic mature stage structure. The problem for this thing in terms of getting more wrapped up and more occluded is that there's a downstream cyclone off the southeast coast of Greenland. And that implies that there's ridginess in between. And I'll show you that from the perspective of Viz 5D in just a minute. So I have to share yet another screen. Someday I'll find myself in the modern era with abilities that actually make sense. So here's the, I think this is kind of cool. You won't see all the screen stuff, but you'll just see that. Here's the, let me make sure I've got this right. Yeah, this is the Viz 5D GFS simulation from 06Z last night. And at that time, the cyclone was at about, these are every 4 millibars. It was, that's 998, 94, 970, 980, so about 978. It's done a little bit of deepening from 6 to 12Z, but there it was off of Newfoundland. And I want to show you what the theta E structure looked like at this time. And there's that. And so this is at 500 meters above sea level. And you see, and I've cut them off at values of 312 or higher. So I don't want to see the tropics just because it's a messy diagram. But there's the cold frontal baroclinic zone associated with this cyclone. Here's a stubby little warm front. And there's the downstream storms off the Greenland coast. And so there's this little hint. It looks like that's kind of an occluded structure in there. Nice thermal ridge. Poshali, Ghosh and I are looking at these things from a satellite perspective with Catherine Naud at City College in New York. And we've developed a mechanism to identify these thermal ridges. The problem is they don't always lead to occlusions. And I can show you some evidence for that here. I'll show you the vertical cross section of theta E. That goes right through that disturbance at that time. In fact, let's click ahead of time. It makes it look a little even more impressively occluded. So maybe at this time. And then I'll tilt up and you can see there's the theta E structure through that portion. Here's the cold frontal bundle of moist isotopes. There's the warm frontal bundle, and there's the characteristic axis of maximum theta E that inhabits the occluded quadrant of the storm. And what we can do is look at the isosurface of theta E, and I'm going to choose the 300 surface. I think it's this one right here that I'm going along the cursor with. And there you can see that perhaps on top of the screen now. And if I tilt it back down, one gets, let me get to the top view. It gets to be a little bit seasick inducing here. I'll get the sea level pressure out of the way. Here you can kind of see what that theta E structure looks like in the vertical. And I've had more experience than maybe most people in the audience, but this is just a canyon in the theta E surface here, as you can see. Let me change the color here a little bit. Yeah, somehow I moved it off. Oh, that's a little bit easier to see what's going on, perhaps. It's a little bit of a canyon in the theta E surface right ahead of this cold front, but it doesn't really wrap up. In classically occluded storms, that canyon goes upward towards the west and northwest, and it doesn't do that in this case. And the reason is because the downstream cyclone is inhibiting its ability to wrap up. So let me step ahead a couple of times, and you can see that it just can't wrap up very much. That's about the peak of how it wraps in. And after that, it just can't do it. And my suspicion is that that inability stems from, here's the 500 millibar map at roughly the same time with the sea level pressure underneath, so you can see where the cyclone is. And you can see that there's a downstream trough and an intervening ridge. And if you put a ridge with a downstream trough in the way of this portion of the storm, which is where you might want to try and wrap up, you're not going to be able to wrap the thing up in a deeply occluded thermal structure. And that'll alter the distribution of precipitation in the vicinity of the storm as well. So it's kind of an interesting picture that's with this relatively normal, average, everyday cyclone. And I want to show you just one more thing that's interesting about it, and then I'll be done. And that is, here's the jet max at about 9 kilometers, probably. What is that? About, let's see, I got to go back a couple times. That is about 250, 300 millibars. So, and here's the sea level pressure again. So the storm center is developing, let's see, I'll just put the lowest sea level isobars there. I gotta do it the other way. So this is just the lowest sea level isobars. This thing's forming right where you might expect it to form. That is in the exit region, the left exit region of this little jet streak. So there's a decent along flow speed change, and you're on the cyclonic shear side. All that looks like it should be the way that things go. But if you look at the vertical motion and the vertical cross section that I cut right through there, look at this. This is all ascent. The ascent is on the anticyclonic shear side of the upper level jet streak. So just take a look at where that is. So, you know, that's the middle of the jet, and all the ascents on the anticyclonic shear side. So that's worthy of some investigation. What's going on there? It's a little bit off of what you might expect, but it's not without physical reason. Here's potential temperature along this cross section. And so you've got, I'm going to zoom in some so you can see it better. You've got ascent on the warm side of this pretty intense upper baroclinic zone, comes all the way down to the ground. So that's a really intense baroclinic zone. Here's the ascent. Here's what the PV looks like in this same cross section. Look at that. I'll get this out of the way just for a minute. That's a pretty intense tropopause fold. And there's ascent on the warm side of it. That just doesn't look like a developing tropopause fold. It's one that's already historically developed, and you've got some interesting vertical motion distribution here. Again, I'm showing only the ascent. I'll take the contour numbers off so you can see the full distribution of the vertical motion a little bit better. There you go. Now, how come this is happening? So what I tried to figure out was, well, let's do this. Let's take a look at the 2D frontogenesis function in this cross section. And I'm showing only the positives. And my guess, and this is only a guess because I tried to figure it out this morning, so you know that's not a lot of time. But here's a region of really intense positive horizontal frontogenesis, probably right about at the jet core and near the jet, because it's right at just the low PV edge of that gradient. And that frontogenetic activity is going to force a thermally direct circulation, and that will, in the poorly stratified air just to the, underneath this maxima, that maybe is what's driving this air to ascend here. So of course, then the next question is what drives this frontogenetic activity? And that'll be the last thing I show you, even though I got some other things ready. I'm going to just show you that. And let's see, I guess it's down at the bottom. That's right. We'll go back to a top view. I'll get rid of the sea level pressure. And here's the 9-kilometer distribution of isobars every 5 millibars. Put the contour numbers back on there. And then here's potential temperature. And look what you have right where there's an upper PV anomaly. I'll zoom in now. You have a really intense baroclinic zone that's being that's subject to differential temperature advection on its. Here's the cold side. Here's the this is the warm side. This is the cold side. When you get on the edge of the cold side, it's suddenly uniformly cold. So you're just piling up isotropes in this bundle by this differential temperature advection. And the consequence is you get this distribution of horizontal frontogenesis at this time. And there's an axis. I'll take some of these numbers off. Maybe there's too many. Yeah, so there's an axis of maximum frontogenesis that goes right in there and it extends into the cross section that's right along that baroclinic zone. So that's pretty neat. And that's just at the tropopause stratosphere boundary. And I think it's forcing air to ascend. And that air that's ascending is directly above the sea level pressure minimum, which is right there. And if I tilt up one more time, get rid of these other things, you can see that's where the vertical motion is.
John.
Yeah. So there's the strong vertical motion sitting right near the core of the cyclone. Yes, Michael.
Yeah, I was wondering. So when you first presented this, you were showing the vertical motion and the somewhat odd location of it being situated near the jet exit region.
Yeah.
And that was the odd aspect.
I thought it was odd that it was kind of on the anticyclonic shear side,
right?
Except when I realized that there's warm air advection in cyclonic shear, then that's what happens.
No, so, I was wondering, is there a way to? This may be going backwards and maybe in the wrong direction with it, but if you see that, if someone were to see that on a map and they say, okay, that's kind of it's a jet exit region, but we have ascent there, well, normally we might expect to see subsidence, just in a very gross sense. And I know I'm not being specific about it. But could it be that it truly isn't a jet exit region, but actually the air parcels aren't the jets moving slower than the flow, so that, or jets moving faster than the flow, so that the parcels aren't actually exiting?
I don't know about that. I would have thought another way to think about what could be going on here is just that I didn't have enough time to do a thorough diagnosis. You could have warm air advection and cyclonic shear. That produces ascent. And I think that's what drives the ascent on the anticyclonic shear side of squall lines in the spring. We may see that this spring. I hope we do. And that can be a really powerful way to get the air to rise in places that just look a little bit odd. When the dynamical diagnosis always leads to an answer, but I don't know if what you said is true or untrue. In this case, it could be, I guess.
Right. But I guess it'd be cleaner if it were a kind of a straight jet without the temperature advections, the warm advection that you're seeing on the anticyclonic shear side. If you were to see ascent in a region near what typically, if you're facing in the direction of the jet, to the right side of this, the end, where you see the isotac, the isotachs are beginning to sort of decrease.
Yeah.
If you were to see ascent on that right side, facing in the direction of the flow, one way to view it is that the air parcels are doing something sort of non-traditional. They're not actually exiting the jet, but the jet's moving faster than the air parcels. It's overtaking it.
Yeah, so you'd have to look at the individual air parcel's acceleration in its direction.
Right, the Lagrangian acceleration would be a little bit odd.
Yeah,
but I don't know if you
could be misled by the traditional analyses and not really get to the core of it, which is the acceleration. Yeah, I think that's possible.
Okay, that may be a really odd circumstance.
It might be so odd as to almost never happen. I don't know that, but it's certainly possible that you could be misled by a traditional analysis. I think that's true.
Okay, all right. Thanks, John.
Yeah, so I'm all done. I'll turn over the screen.
All right, thanks. All right, I hope I get this right. I have two desktops like John did. I don't see my desktop too. Oh gosh, here we go. I'll do this. Okay. So good afternoon, everyone. first, again, I always start with John's favorite map, which is the meteorogram. And so we're looking at
meteorogram.
Meteorogram, John,
Oh,
meteorogram. Or just call it a time series. And so we're looking at the temperature in the upper part of this image. The next part is the dew point, and then finally the precipitation. The red contour being the 3-hourly precipitation rates, and the green, the accumulated precipitation along the 60-hour forecast time period from a model the MM5 initialized at 12Z this morning. And so what you can see in this diagram is, warmer times ahead in terms of, at least relative to today, tomorrow perhaps being a bit warmer, and then with the precipitation, presumably some clouds, we might stay actually in that upper 30s to low 40 range. Whether this is rain or snow is something to we can peek at, but the weekend looks generally dry, and these precipitation rates might be might be an overestimate of what we're actually going to see. Another view of the forecast for precipitation, I'll come back to the MM5 in a second, is when we look at the output from the short range ensemble forecasting system that NOAA maintains, and we look at the total accumulated precipitation. We see those two sort of ramp ups in accumulated precipitation overnight tonight, and again during the same time period, Saturday night into Sunday morning, with a little bit more precipitation. This ends up giving us an accumulated precipitation, at least in the ensemble mean, on the order of about 0.2 of an inch. The MM5 was about 0.15 of an inch. So it's about the same in terms of those amounts. If you look at the total snow, how much of this might be snow, maybe 0.5 inch or so in terms of the ensemble mean, but you can see considerable spread. But a lot of these ensemble members close to zero in terms of total precipitation or even snowfall. So the weekend doesn't look like it's going to be necessarily a washout by any sort, but we also want to come back and kind of get a sense of what are the factors that are contributing to that precipitation. Well, certainly we're going to need vertical motion, so we're going to go back, look at the time height section for the same period for this run. Again, we've seen these before. The yellow contours are the isotropes. Time runs from left to right on this image. The red is the relative humidity, everything contoured above 70% in red, or everything that's contoured is 70% or higher. Vertical motions, in this case, minus omega. So ascent will be the solid contours, blue contours, descent, the negative blue contours. And then finally, the tropopause, dynamical tropopause in green in this cross section. And you can see the what looks to be the approach of a weak upper trough over us around midnight tonight, actually the trough axis going by us, and a nice couplet, at least in terms of the vertical motion, the ascent preceding it. You can see the column beginning to moisten up as the relative humidities go up, as the air parcels are ascending and they're reaching they're approaching saturation. We see that, and that's going to be this approach of this upper trough will be one factor that may give us a little bit of light precipitation. Followed by that, around midnight or so, early morning hours tomorrow, we're going to see subsidence spreading over us, the column beginning to dry out, at least in terms of, or lower relative humidities during that time period. And then another period of vertical motion, and we'll look at some causes for that. That seems to be well in advance of the lowered tropopause, so that you can see it's kind of a different configuration between tonight's passage of a weak upper trough-like feature, and then the pattern that's going to occur during the day, Sunday, during the day on Sunday, when we might get another brief, early Sunday morning, this other brief period of precipitation. So that's kind of the setup for that. The first map that I want to look at on this is we're going to go to the surface map, forecast surface map for 6 hours today, and I'll actually advance it so we have the right time on it. This is for 18Z today, and you can see across the United States this broad anticyclone. We saw the precipitation area that was the remnants of that convective area that caused the hail that Professor Rao showed earlier, and John was looking at the frontogenesis in the southeastern part of the United States along this boundary that may have been contributing to the continued precipitation along this old warm front. But for us, you can see it's relatively quiet. And one of the things I want to first point out about the relative recent warmth that we've experienced is something that Greg has talked a lot about, and it's related to these plumes that emerge from the tropics and subtropics. And I'm going to immediately go, I don't know why this is acting this way, to this morning's dynamical tropopause map. This is a map along the surface of constant potential vorticity. And we're looking at pressure, the isobars on this. So you can, if you trace along the this map, you can see the pressures, relatively high dynamical tropopause. But look at this broad sprawling area of very high dynamical tropopause over us. And if you look at these, the colors on this map, and I'll go just from a slightly different perspective, we'll look at a view over the continental view. You can see what you might expect during this time of year. And let me just get this back to the initial time. This is jumping around quite a bit. As you look at this map, you can see that when you get into the tropics, the tropopause is going to be relatively high. You kind of expect that in terms of the pressures being low. And as you get further closer to the poles, the tropopause elevation decreases in terms of pressure. You're seeing increasing pressure there. So the air that we have over us is more characteristic of air that might be found at lower latitudes. And as we animate this, you're going to see these surges of, I would call it subtropical-like air from very low latitudes into our vicinity. And the weather that we've experienced over the last few days has been much above normal, or certainly above normal. I think is due, in fact, to a surge of this bubble of air that's moved in from lower latitudes into our latitudes. And I think it's kind of interesting. I'm becoming more of a convinced that some of the things that Greg has been talking about, that we've basically pushed, the regime that we're in might be more typical of what's going to be 10 or 15 degrees further to our latitude, further to our south, in terms of the weather we're experiencing the last couple of days. If I were to step forward in this, which I will, just to get a sense of where these surges are emanating. I don't know why this continues to advance. Again, one, you can just get, this is like you're looking at one of the rotating tank experience, but you can see these surges of air that had their origins at very low latitudes. Some of them not quite surges out over the Atlantic. You can see this getting swept up over Greenland. But you can see also for over us over the course of the next several days, over the next week, we're going to be in a situation where we have this more subtropical-like air along the dynamical tropopause over us or to our north. And that would portend that we're going to be perhaps much warmer than normal if you just draw an analog between what we've seen in the last couple of days. But you can really see nice structures in the evolution of this dynamical tropopause over the next, again, this is over 300 some hours in the forecast, and we're starting this over again. So as you sweep through this, you see a feature passing by us. That's the one that's going to give us some weather on Sunday. So Sunday into Monday. And then once it gets by, we're going to see the dynamical tropopause again raising again. And that's going to be accompanied by, again, an increase in temperatures over us, even at the surface. And I would argue that if we didn't have the snow cover at the surface, we'd probably be easily 5 or 10 degrees warmer than we have been with this air. So let me go back to the surface map and talk about the two precipitation events that are coming up. And we'll look at some Q vectors and GEMPAC to look at one way of looking at some of the forcing for that. So I'll go back to our national map. And again, if there's a question, please ask or a comment about that. But again, you can see this broad plume of air that had its origins at lower latitudes.
Michael, I got a question.
Yeah.
If we go back to that big view for just one still image, it doesn't have to be the animation if you can do that. It seems to me that the that view is really instructive. You get all these really small scale PV substance maxima. And yet when you integrate them all together, not only because you have to do an inverse Laplacian, but it's the Stokes theorem problem on top of that. What does the circulation look like from the collection of all of these disturbances? And because the reason I ask is because what happens, I think, when we get to this point in the year is that the intense circulation that's driven by the cold pole starts to shed circulation substance. You see these cutoff PV features heading equatorward where they just, they have a cold air dome underneath them and they just get obliterated. And that subtracts almost by 1,000 cuts the circulation at high latitude. And I wonder if one could actually quantify that from a day-to-day point of view, as you transition from the winter to the spring and actually see the aggregate circulation weaken and put your finger on the disturbances that are doing the weakening.
Well, I wonder if I see your point. I think I see your point, but I wonder if is it the disturbances doing the weakening, or is it? I mean, you're shedding these local maxima these cold blobs along the dynamical tropopause as they go to lower latitudes. But they ultimately, their decay is more radiatively driven, right? Because
Yeah, that's right.
that's the only thing that's gonna warm up the dynamical tropopause, since it's a conserved variable, would be radiative processes. So I think you could probably do some sort of budget of these, and I think the tools that you developed with the identifying the contours and the equivalent latitudes might be one way to do it. But I don't know can you track cutoffs well with this?
I haven't put it to the test, but I think I could. I'm pretty sure I could, because it's almost never are you along a longitude line going to have an intercept, a 4 valued longitude line. Usually it limits at 3. I wonder if it gets a little bit crazier in the spring, but that would be the trick. You'd have to just figure out what's the maximum limit of the number of counts you got to make along a longitude line. I don't think it would exceed 4, but I don't know.
I think you're
too weedy. Yeah. I know what I'm talking about. Nobody else does, because I've developed this stupid technique. So,
but I think you're right that you could probably do so look at a collection of these smaller pieces that break off, and the integrated circulation around them must be related to the overall decrease in the circulation at higher latitudes that you're seeing as you proceed into a warmer season.
That's a good way to state it. It's perfectly concise. That's exactly what I'm wondering. Would it actually look like that, almost linearly? I think it probably would.
And then the interesting questions, if that were to verify, is what's the rate of decay of the circulation, and can you measure it by how many of these break off, and what's generating?
Absolutely.
Going back to your original question, what is the process that leads to the generation of this sort of ripping apart of the polar vortex?
Right, and then you could ask, what's that look like in a long time series of several, of 100 matches, whether in real reanalysis or in a climate model? That'd be really an interesting problem.
Right.
So, thanks. Sorry.
Oh,
Can I mention something? Yeah.
Please.
Yeah. These past couple days, I think I mentioned this last week, the polar vortex has been shifting again from what it's been over the past month or so. And at this point, it's still sitting over the poles, but it's moving toward Asia. And it looks like, if you believe the progs of GFS, it's going to move back off the poles over Asia again, and then interfere with the subtropical jet over South Asia. But that's weird. But in the meantime, the way I see what you're looking at right here over the U.S. with this intrusion is kind of a plume, tropical plume that's come in to fill the void as the polar vortex is moving out. And what I'm saying is it looks like it's a breaking Rossby wave at this point, where you see it right there going up. It's going to kind of keel over and break into the Atlantic. And so it looks like it's something moving into the void behind as its pattern shifting. The way it looks now is that it's shifting into a pattern where we won't have the polar vortex near us anymore, and it's just going to stay fairly warm. But I see it more as a void than really a system coming in.
Right. And so this is the mass that was over us moving eastward, and I don't know why this is behaving this way, but as we go forward in time, look what's happening over the west coast of the United States as this next little plume comes up. And I seen this in the forecast a week ago. Last week I didn't get to those in the series of maps that I was showing last week, but that's a really persistent feature. And then once this begins to arrive and we begin to warm up, this is Tuesday into Wednesday, I'd imagine we're going to see a nice big jump in temperatures over us during that time period. And as Greg was saying, we don't really see much of these blues and greens over us so much as they are over the western, the other hemisphere.
Yeah, you can see the whole polar vortex has shifted over at that point.
Yeah, it's a really interesting view there. But I want to quickly just get back to the precipitation over us and just show two quick views in the forecast, and then maybe show a little bit of GEMPAC along with this. So this is 6-hour forecast, and you can see the arrival of the very light precipitation. Again, this is pretty spotty. It kind of, as it arrives, it's just going to be just to our south and east. We're going to be on the edge of this. A different view from the NAM forecast for the same time period this evening. What's that, John?
Just like that little cyclone over Anchor Desai land in Upper Peninsula, Michigan.
Yeah, we're going to see that again. Yeah, there's that precipitation. This is again early Saturday morning. And you get a burst of precipitation as this goes by, but it's relatively weak, and the accumulated amounts are pretty small. So again, this doesn't look to be a washout at all for us. And if I just continue moving forward in the NAM forecast, you can see the next area of precipitation is developing, and we're going to actually be, oddly enough, in a warm sector over this weekend on Sunday as this cyclone develops to our north. But the central and northern part of our state are going to be experiencing some snowfall, but we'll be largely dry, maybe a little bit of light precipitation as the cyclone goes by us. One of the things I wanted to look at was just, these are very weak and indistinct features that are responsible for the precipitation. We saw evidence of an upper wave in the time height section going by. Obviously, there's not much going on at the surface. It's relatively weak. If we look at the Q vectors from the aviation model, the GFS model, the global forecast system model that's being run, these are Q vectors for the period. This is a 12-hour forecast for them. Again, very weak patterns. And since we're, perhaps looking at upper trough being the responsible feature and not something at low levels, we're not going to expect to see much with the arrival of this, as this wave goes by. This is 12 hours in the forecast, so this is valid at midnight, 0Z. If I were to advance this map, is it set up? Let me just do it again. 12 hours to F60. I'm going to first run it and then step
Michael,
forward.
we're still seeing the surface map. I think you might be
That's right. Let me stop and then re-share. Thank you. Thanks for mentioning that. Now you should see it. Yeah.
Yeah.
Okay. So I'm going to go to the 12 hours into the forecast. I'm just trying to step forward. It's just a little bit lagged. Go back. This is this evening. Again, the pattern of these Q vectors is pretty indistinct. This is at 850 hectopascal. Remember, for those that have had 452, Q vectors are a measure of the vector rate of change of the potential temperature gradient. We're looking at these Q vectors calculated using the geostrophic wind and theta at 850 hectopascals. And a very, I would say, disorganized pattern on this map. And it would have been better if I had also put on the actual convergence so you could see that. And you also want to see this over some depth of the atmosphere. So if we step forward in time, this is at 18 hours in the forecast. Again, very, not a very distinct pattern on this particular map at this point, and that weather system is moving eastward. We saw the generation of a weak low in western Michigan, and that's perhaps due to this Q vector convergence that's beginning to show up on the eastern shores of Lake Michigan. That will be associated as a forcing, QG forcing for vertical motion, ascent, and vortex stretching. So that might be one of the factors that was associated with that. But if we just continue stepping forward, the interesting and more interesting pattern begins to emerge in the forecast a little bit later on. You can see the baroclinic zone that's over us. You can see, again, this is at 36 hours of the forecast. This is tomorrow evening. Nothing just yet. I'm just trying to get it. But you now see this more impressive area of Q vector convergence to our northwest by the time we get into Sunday morning. As we step further, you can see the emergence of a pretty well-organized baroclinic zone between those two time periods. This is 12Z in the morning, and a nice cold front and cold frontogenesis occurring. You would expect to see a band of precipitation along this developing cold front. In the northern part of the state, where we saw the cyclone beginning to develop and the area of snowfall that was forecast by the GFS, that shows up pretty nicely as well with this pattern of Q vector convergence across the northern and central parts of the state by this time. If I go back to, I have to switch between maps, I should be showing everything, but just keep this picture in mind. Again, nice baroclinic zone, Q vectors pointing from cold to warm. So that's a frontogenetic signature, and the Q vector convergence to our north and to our northeast. Let's look at the forecast at that time period. And I'll reshare this, bring up our map. And I'll match the times and the model so we're not mixing apples with oranges. And so we get to 48 hours in the forecast. Again, you can see where the accumulated precipitation is again, a fernogenetic circulation setup with the winds, and you can see at least the thickness contours. And you can see very nicely where we saw that pattern of Q-vector convergence, the associated precipitation. And I imagine the stability is weaker here, so we're also getting some convective precipitation along it. But this cyclone is going to pass by to our north. The Q-vector convergence pattern we saw was to our northeast. And so we'd expect in the intermediate times, this low is going to track in the region where we've seen the largest ascent in the lower troposphere. So a really quiet pattern for us. Once the weather system moves by, we saw that we're going to get a lower tropopause height over us. That's going to get colder, but then you'll see the return to a much warmer pattern. And once we get past Tuesday, so there's the anticyclone building in, and then you can see as it slowly moves out, a nice return flow, west-southwesterly flow over us. We begin to warm up. It's going to get pretty decent. In the sort of hazards outlook, that slow-moving baroclinic zone, sorry for this moving around, is the potential for flooding rains across the southeastern part of the United States and sort of severe drought conditions remaining out over the western United States. That's days 3 to 7. And if we want to look ahead beyond that, again, a quiet pattern across the entire country with maybe some windy conditions beyond that over the the northeastern part of the United States. Very last thing I want to show, just as we go into that time period, talking about predictability a lot in the last couple of weeks, just another view of the predictability of the flow. We're looking at the GFS ensembles with two different contour sets, the 552 decameter contour and the 576 decameter contour. This is the forecast for day 3. Again, there are lots of ensemble members here, over 20 members, and we're looking at just one contour plot. The closeness of these contours indicates, by some measures, if we have a good sample, a high predictability of the flow where the contours are more spread apart. You see a lot of variation in their location, indicates less certainty in what the flow pattern is going to be as measured by these contours. And you can see at least through day 3, we have a pretty good sense of what's going to, the models are pretty consistent, I should say, with the forecast. Again, these are based on initial condition perturbations. Going to day 4, again, sort of very similar structure, but you can begin to see maybe a cutoff forming off the west coast of the United States, or just more of an open trough over the western United States. How these translate into actual weather is certainly a big question. And going out to day 6, again, looking at these maps, you can see some variation in the position of troughs, the timing of troughs, but generally westerly flow across the high latitudes over us at 550 on the 552 decameter contour, and as well at low latitudes with maybe something that's more in the subtropics. So westerly flow certainly is going to translate into, in general, to warmer weather for us, or relatively warm weather for us. And so it looks like the week ahead is going to be nice. So 2 bursts of precipitation over the next 60 hours, a little bit tonight, particularly over the southeastern part of our state with the passage of that first upper trough. Not much going on in the lower troposphere, and then another round of precipitation as a cyclone begins to develop over us. But that's largely going to be precipitation well to our north, with where we saw the Q-vector convergence in the track of that cyclone. And the attendant cold front is frontogenetical, but well to our south. So that's where the heavy rains are going to be over the southeastern United States. And then after that, we get chilly for a little bit and then warm up for the latter part of the week, which looks pretty good. And seems like, I don't say it's a lock, but it's certainly we're going to be warming up. Any questions or comments? I know it's a little late.
No, I think that that ensemble stuff is really cool. There's a whole bunch of extensions one could make to it if you had the information at your fingertips, to run through. You could find the jet axis and see if that differs more than the 500 millibar, somewhat arbitrarily chosen geopotential height lines and so on. That would be really interesting.
Yeah, another thing that would be interesting is if you have the forecast, looking at measures that you track, which are like the 850 cold pool.
Oh yeah, you could do that. Yeah, that's right.
For each of the ensemble members, and just see the predictability of that and how that relates to other aspects of the flow regime.
Yeah, and in fact, a secondary question would be if you split it up into regions. Certainly, a regional forecast would be more of interest to citizens. But a forecast of the actual cold pool area for the whole hemisphere, I guess, would have less variance than regional forecasts. And it would be really nice to know that, to really be able to say, sure, that we can make a decent prediction a week out of what the hemisphere is going to do in its evolution, but we can't necessarily say what it's going to do over North America. That would be really cool.
Right. I think we get that data. Pete could speak to that, but I think it'd be interesting as you do your map, you show those charts for the graph for how far into the season we are, extending them beyond that with the ensemble information.
Yeah, right.
And having the uncertainty associated with that, and then just that might be a neat addition to it.
Right.
What I have up here, just out of curiosity, is the snow depth over the U.S. This is forecasted. I was really delighted on the 12Z and 18Z forecast from yesterday. Showed it totally going away from our area by the end of the period with no new snow. But and I haven't seen the 12Z for today, but I know the 6Z last night brought some more snow in here. But again, if you want warmer weather, you got to get rid of the snow. That's at least one of the critical elements. And this forecast actually looks pretty good. I know John has said that he's tired of snow. He doesn't want to see any more for at least another 2 or 3 seasons. So
I think you're concentrating on the wrong part of that imagined sentence.
But anyway, thanks, Angela. Thank you, John. Thanks, Pete, for setting this up, and Greg's the comments, and just everyone that participated in this today. Stay safe and have a great weekend.
Thank you, Michael. Thanks, Angela. Thanks, Pete.
You bet, you guys. Thank you.